Hey, so next I'm going to talk about the dot product. Now you're hopefully familiar with the dot product, but the problem I have with the dot product is most classes, most of the way we learn it, it doesn't give you any intuition about why it's important or how it works. So my purpose here is to reintroduce you to the dot product and hopefully build that intuition of why you'd want to know what it is. Now I'm going to introduce the non-standard form. Well, it's I think it's the better form for understanding, but it's not what you typically see at the beginning. So the dot product of two vectors, if I have vector p and a dot product with a dot here with q, is the length of p times by the length of q, and then times by the cosine of alpha, which is the angle between the two vectors. So I'm going to draw that out. So here's my coordinate system. I have a vector p, I have a vector, it's a p, q. There's an angle between them, that's alpha. So if I take the cosine of that angle between the two vectors, I multiply that by the length of p, length of q. That's what my dot product is. So the dot product becomes really useful. The first thing I want to highlight is this cosine component here. Now let's draw out a cosine. So here's my my typical angle. This is my angle here, and then my value of the cosine. And remember, cosine and sine go from 1 to -1 like that. Cosine starts at 1 and has this kind of funny shape. Bam. Okay. Now I'm going to highlight some important points. This is pi. This is pi over 2. This is 3 pi over 2. Right? Look familiar? This, it equals, gotta fix that. It equals 0 at that point, -1 at this point, 1 at this point, 0 again, and up to 1 here. So that's important to refer back to. So I painted that there, and we'll come right back to it in a second. But first, I want to talk about some of the important rules or properties of dot products. The first one is if the vectors p and q, if they are orthogonal, if there's a 90-degree angle between them, then the dot product of p and q is 0, just like that. Cool. So I'm going to draw it out, and what that means is if I have two vectors, I'm going to put p here, I'm going to put q there, and if they're orthogonal, if the angle between them is 90 degrees, they're 0. And now that we've talked about this cosine business, we can see why. If the angle between these are exactly 90 degrees, so right here, or negative 90 degrees, right there, then the cosine is 0. If this cosine is 0, this whole formula is 0. So it's easy. If the vectors are orthogonal, the cosine is 0, the whole thing is 0. Cool. If my vectors are orthogonal, the dot product gives me 0. If p and q are codirectional, it's kind of like collinear, except they're not points, they're not lines, they're vectors, so they're codirectional. So if they point in the same direction, then p dot product q just equals the length of p times the length of q. And again, looking at the cosine here, we can see why. If they point in the same direction, the angle between them is 0, right? If the angle is 0, the cosine collapses to 1, and it goes away. It just goes away. So it's the length of p times the length of q. Cool. If the p and the q form an acute angle, remember, an acute angle is less than 90 degrees. So we have an acute angle, plus or minus. So let's draw that out here. So if I have p here, now I'm going to draw, just for illustrative purposes, I'm going to draw the orthogonal line to p. Now if q is anywhere on this side of this line in terms of direction, then p and q form an acute angle. And if I come back here, and I'm going to draw, just to avoid making it too messy, I'm going to draw my cosine again. And I'm going to draw a bit extra, so my 0, like that. Now, this is my pi over 2, which is my 90 degrees. This is my minus pi over 2. So if the angle between them, if that alpha is anywhere in between this 90 degrees and negative 90 degrees, then the cosine is positive, right? If the cosine is positive, that this is positive, this, or their lengths are always positive, then the whole thing is positive. So if P and Q form an acute angle, our knowledge of cosine tells us that dot product of P and Q must be bigger than 0, right? We've learned that if it is 0, they're orthogonal. If it's bigger than 0, they point in the same direction, general direction. They point in the same general direction. Cool. And then likewise, if P and Q form an obtuse angle, right? So if Q is pointing more than 90 degrees away from P, if it's an obtuse angle, then what happens? Then our cosine falls into this other territory here. Negative, okay? The cosine becomes negative. If the cosine becomes negative, the cos of alpha is less than 0. Then dot product of P and Q is less than 0. I should write this up here too. I don't know why that eraser keeps coming. Then the cos of alpha is bigger than 0. So I'm going to highlight all these rules, right? So this highlights just how powerful the dot product is. If I just take the dot product of two angles, I can tell it whether they're orthogonal or not. It gives me a 0. Whether they're co-directional, whether it gives me just the lengths multiplied together. Whether it's an acute angle, if it's bigger than 0, or an obtuse angle, if it's less than 0. So we can quickly tell if something's pointing away, pointing together, pointing the same direction, no matter what the vectors are, just by doing a dot product. So dot product is awesome and it's really powerful. Now the problem though, if I come back to this formula here, it requires length, and cosine. Length requires a square root. So this requires 2 square roots and a cosine. That's slow. Problem. Calculating 2 square roots and a cosine is slow. Because graphics, we need speed, right? We want everything to go fast. That's a real problem. Luckily for us, there is a better way. So this better way is typically how it's taught because it's simpler. The problem I have is people memorize the dot product formula and have no intuition. They don't understand what it means. If you're going to memorize anything, memorize this here, okay? Memorize this, because that tells you what the dot product does. It tells you how to use it. It tells you what it means. When you go to implement it, then you can do the simple method. The simple method doesn't help you build that intuition. If you memorize anything, memorize this. So let's introduce the simpler method. But again, falling in line with this idea that I want you to develop this intuition, I don't want to just show it to you. I'm going to do a quick mathematical proof. So I'm going to do a very quick proof of a better way. Right? So you believe me that these are the same thing. So I'm going to start by drawing out a triangle. Okay, now what we're doing, I'm going to call this P. You know what, I'm going to, that's okay, Q. Now, the first thing I'm going to write out is what's called the law of cosines. Don't worry, nobody memorizes this stuff, unless you're a math major. But it looks kind of like this. C squared equals A squared plus B squared minus 2AB cosine of C. Now I'm going to start filling this in a little bit. In this, the C is referring to is this C here, of course. The c it's referring to, the small c, is this c here. It's not going so well. There we go. That's the c we're referring to right there. And then that's this one. A is this, and B is this side, and this angle here is the big C. Or the other c, doesn't really matter. So I'm going to rewrite that with our properties. C squared is this one over here, right? So to get the length of that side, I can just do P minus Q, right? I can write that out as P minus Q. These are my vectors. The size of that. I'm going to cut the angle signs because this gets messy, but these are vectors, okay? So P minus Q is the length of that, gives me that C equals A squared. That's going to be vector P, the length of that. You know, I did make a mistake here. Just for simplification, I'm going to draw that on the origin. Nothing else changes. Okay. So, yes. So A squared is going to be the length of A, P squared. I gotta turn off that feature. Length of P squared. And then B is this one down here. So that's the length of Q squared minus 2AB again. A is the length of P. B is the length of Q. Cos. And C in here, I'm going to call that my alpha. Awesome. Cool. Now the first thing I want to highlight is this right here should look very familiar. We have a definition for us. If I go back up here, haha, that is our dot product, P, Q, cos alpha. So I'm going to rewrite that already as the 2 and the P dot product Q, right? I can replace that already. That's great. We have already defined this. Okay. Now I'm going to start rewriting and rearranging this. I want this to be on my left. So I'm going to put it over here. P dot product Q, these are my classic dot product, equals, and I'm going to start copying this out. P squared plus this length of Q squared minus 2. Well, let's wait a second. Let's make sure I'm not missing anything here. Yeah. Yes, okay, that's good. I got confused for a second. I'm going to bring this PQ over to the other side. So that's minus the length of P minus Q to the other side. And then I have this 2. So when I brought it back over, I'll just put 1 over 2 on this side. You can pause the video to make sure I have it right. But yeah, I did it all in my head, so it must be right? So this is the same thing. I'm just rearranging. And now let's just do this wonderful algebra. Let's write it out. The first thing I want to highlight is this. P squared. Now, to remember, the size of P is px squared plus py squared square root. But I'm squaring it. So look at that, I square. That will cancel out. The same thing for the Q, size of Q squared. The size of Q is qx squared plus qy squared square root. But I'm squaring it. Awesome. Minus P minus Q, the length of P minus Q. Aha! I forgot a square sign. I knew it. So it was C squared equals, so P minus Q squared equals. So yeah, square. Sorry about that. Minus P minus Q. I got flustered there. There we go. Okay, so P minus Q squared, the length of that squared, so PX minus QX squared plus PY minus QY squared, all square rooted, and again squared. And that's still in those big brackets. So I'm going to cancel out those square root and squares and rewrite it really quickly. We have lots of space. So I'm left with PX squared plus PY squared plus qx squared plus qy squared minus, and I'll put this in brackets. I'm going to expand this, px minus qx squared. That's px squared minus 2px qx plus qx squared. And then this one's the same thing. It's py squared minus 2py qy plus qy squared. Bracket, bracket. Cool. Whew. The next thing you should notice is these start to cancel out. Look at that. Px squared, that's a minus, minus px squared. Py squared, that's a minus, right? Because of this minus here. Minus py. Qx squared cancels that one. Qy squared cancels that one. Remember this minus here? So those pluses become minuses. So what am I left with? So that all canceled out. I'm just left with 1 over 2. Okay, this is all gone. And then there's a minus sign, so I'll flip it as I go. This is 2px qx, and this is 2 plus 2py qy. Okay, 2, 2.5, that cancels out. All right, so then the dot product of pq is just px qx plus py qy. This is an x. So this is probably, if I go to this is probably the dot product formula that you would have learned in your linear algebra class. And if you want to implement this and code it up, yeah, that's probably the version you want to code. But I went through this process because I wanted to show you that this is just a simplification. This definition up top here is what we care about. It's the length of p times the length of q and the cosine of the angle between them. That is your intuition. If you know that, on a test, in your code, you can figure out what the heck's going on at any time, as long as you know it's implemented properly. And all of these cool rules still apply. Now, I will also mention that this is the 2D version of the dot product. Luckily, and I won't do the math, this just generalizes, okay? So it equals the sum of I equals 1 to n of pi qi, just like that. And so with that px, y, z, however, I, j, k, whatever dimensions you have, you just add them up. All right, so this is a really powerful thing. Just by doing a multiplication, another multiplication, and an addition, we can find out whether angles are orthogonal, codirectional, whether they form an acute angle or an obtuse angle. So I think that's a really, really powerful thing, and we're definitely going to see more of the dot product in this class. All right, time for a break. We'll be back in a bit with cross product.